Okay, hello everyone. My name is Miguel Palhas. I work at a company that you may have seen in a booth over there called UTrust. We're a company in the blockchain space, even though we're not actually implementing our own blockchain, we're just using it. So I'm here to talk a little bit about smart contracts. If you want to know more about UTrust or about blockchain in general, you can talk to me or to anyone in the booth later on. This talk is going to focus on a very specific technical part here, which is smart contracts. Just so you know, are you developers or non-developers? Okay, there's a bit of a mixed group, okay. So the idea is for me is to explain smart contracts in a way that's simple to understand. I'm not going to go too deep into the technical stuff, but just a developer-oriented view of what they are and what they're useful for. So, and about cryptocurrencies in general, are you familiar with? I mean, Bitcoin. I'm sure everyone has heard of by now. Ethereum, I'm guessing it's pretty famous as well. There's a few other ones which I don't really care about. There's even a few very funny ones which no one should care about because they're only there to steal your money. This talk is not gonna touch into any of this. I don't really care about the whole economic part of this. I'm just gonna focus on Ethereum specifically and on the technical benefits this can give us. Because besides this whole technical and scamish market, there's a lot of really interesting technical stuff and interesting technology that can be useful in the future. So this is crypto, a lot of random coins floating around and people scamming other people around it. But the underlying technology, the blockchain, is what I'm going to be talking about today, more specifically about smart contracts. So besides knowing what Bitcoin is, does everyone know or has any idea of what a blockchain is or how it works overall? Blocks showing up every few minutes or something. Okay, so a blockchain is pretty much a decentralized peer-to-peer network. There's no central server or anything. Everyone has the same power. And it stores an immutable list of transactions, so everyone just sends transactions, and it's like adding new transactions into a book. You can add new transactions, you can never delete them. It's append only. Everything that's written in there, it can never be reversed. It's also the first solution to the double spend problem, which is a technical problem in trying to implement digital currencies where usually there's bugs or exploits you can take advantage of to spend the same amount of money twice or spend it in order to get your goods and then undo the transaction. There's a few quirks in distributed systems that sometimes allow you to do that. It's unhackable because, well, nothing really is, and we'll see later on why. But theoretically, it's pretty safe because of the whole being distributed and then decentralized and all those buzzwords. There's a lot of other buzzwords that you may have heard about wallets, Merkle trees, proof of work, but just a bunch of cryptography. Again, I'm not going to touch into any of this today. Feel free to ask me later about this stuff. I'm glad to answer. But now I'm going to focus on a very specific part. So let's say we have a pyramid, and pretty much like for the internet, we have a pyramid where we have the hardware layer underneath, all the servers that are powering the internet, and then we have the HTTP protocol and IP protocol and so on that only us developers really care about and know how they work. And then on top of that, you have Facebook and all those other things that people use. And people that use Facebook don't need to understand how these bottom things work. So the same thing happens for the Ethereum blockchain. So we also have, we can call it the hardware network, which is all those computers powering the network. On top of that, we can have a layer of consensus, which is that the mining algorithm, proof of work, proof of stake, all those algorithms that are ensuring that the data that is there is kept there and is irreversible and is shared across the entire network. But on top of that, we can add a semantic layer, which means that we can create some kind of program or code that gives meaning to those transactions, to that random data. And with that meaning we give them, we can create beautiful distributed apps like trading cryptographically secure kittens online. And this is where I'm going to focus today. So to understand what a smart contract is or how it works, we don't need to understand how proof of work works or why Bitcoin is distributed or anything like that. We just need to trust that it works, kind of, and this layer above abstracts away all of that. So going a bit further into Ethereum, which is the second most popular cryptocurrency and the first one to implement smart contracts. So Ethereum, even though it has its own currency, it's not there for the currency, it's there for the technology and to empower other developers to create apps in this network. And the concept of Ethereum, and to understand what a smart contract really is, we need to go to the concept of a transaction. So most people, when we think about a transaction, we think about this, just transacting money to some other people to buy something or for goods or services or whatever. It's a monetary transaction, but every developer knows that a transaction can be much more general like this, can be something like this. This is also a transaction. In this case, it's a database transaction. And what it means is I'm not transferring money to anyone, I'm doing a change of state. In case of a financial transaction, that change of state is I had $10, now you have $10. In this case, the username was whatever it was before, and now it's this. So there was a change of state. And the financial transaction, which is what you do when you spend some money, is just a specific case of a general transaction. And as I said, Bitcoin and Ethereum, they store transactions in a blockchain. In case of Bitcoin, more or less, it stores monetary transactions, people trading Bitcoin with other people. In case of Ethereum, we can also do that, but we can create general transactions where we just change states and we decide what meaning we give to that state. And from there, we can implement whatever we wish. And we get all those benefits that the network provides, abstracts for us about the decentralization, the trust, the ability to trust that those transactions are irreversible and verifiable by everyone. And that's what a smart contract really is. It's a program that changes states from time to time and stays and lives on the blockchain so that everyone can publicly verify the data. So a smart contract, yeah, like I said, it's a program. It lives in the blockchain and it lives on its own. This part is important because it means once you create a smart contract and we publish it on the blockchain, we don't have any more control over it as any of the other users. I mean, we can implement some security mechanisms to give ourselves control, but we can't change the code for a smart contract. We can't delete it. We can't fix bugs, and that's one of the problems, actually. But the smart contract is an entity by itself. It's a first-class citizen, and I'll show later on why this is important. But it's important to understand that the smart contract is not ours. It's public for the blockchain like everything else. The smart contract will keep its own state. So in developer terms, this means we have instance variables or whatever, and we can mutate that state however we want. And the code itself will define the rules to change that state. And from this we can create very simple but very powerful programs and take advantage of the security benefits and the trust mechanisms that the blockchain provides for us. And the usual question is, what is this for? And the usual answer is that we can implement everything in a blockchain now. We can build banks on a blockchain, insurance systems on a blockchain, and everything on a blockchain. Just like a few years ago, we could do everything as a service. In reality, I think what we can use blockchains for is to abstract away kind of the trust part of a system. So again, going back to the financial system example, which is the standard one, right now we have to trust our banks that they're going to keep our money, that they're not going to go bankrupt, or that they're not going to spend it somewhere else, or that they're not going to just lock our accounts for whatever reason. I mean, we can, I guess, trust our banks to a certain degree, but it's still some trust that we have to give a third party. Sometimes we may not want to do that, or we may just not be able to trust the other party, if it's not a bank, if it's a business partner or something else. And with these guarantees that the blockchain provides us, we can implement whatever decisions we want, whatever rules we want for our system, and we don't have to trust the other party that he will keep his end of the bargain. We can just agree that the rules are there in the smart contract, and the blockchain will make sure that those rules are kept. And of course, one of the basic examples for this are economic systems, implement money. That's what everyone hears about right now, Bitcoin, Ethereum, and so on. Insurance policies, this is a bit far-fetched, but theoretically, since we can implement any kind of rule in the blockchain, we could theoretically have a smart contract that defines what the rules are for someone to get to apply for an insurance, to how much money he would get back in specific situations. Here we get to the problem of how we interact with the real world. So if we had a car insurance company, how would we prove to the blockchain that the car really crashed and that the fault was not this guy and was the other guys? This is the actual problem with the trust of the blockchain, is that we can trust all the data that's in the blockchain itself, but when it comes to proving data from the real world, that's something the blockchain can't do. So this is I think where I would draw the line. It's still a possibility, and there's a lot of things in the insurance business that can be done here, but there's this gap that still isn't filled yet. But then much more simple examples, and this is one of my favorites. We can do something like what's now called proof of existence, where we can, for example, to prove that at this point in time I own a specific document in my computer, I can do something as simple as create a hash of that document, store it in the blockchain, and I mean, I could later brute force that hash, but assuming we use a hash that's secure enough to beat the test of time, a few years from now I can just show that that block existed at the time. All blocks have a timestamp and we can know when they were mined. And by having that hash and by having the same file and proving that the hash of that file matches, in a way I'm proving that at this point in time I had that content. This could be something very useful, for example, for copyright infringement, to prove that I was the first author of a specific document or something. This is actually a use case that I think could be really useful. And there's already a company doing something similar to this. They're using the Ethereum blockchain to track the lifespan of diamonds, and in a way to prove that everything from the mining of the diamonds to the manufacturing to the sale of that diamond. And this is very important in the diamond business and other jewelry, to prove that they were not blood diamonds, so mined from hard labor camps or something, or slavery. And so when people buy a diamond using this system, they can prove through the blockchain that the diamond went through a legitimate process and was not caused by someone's death or something. And let's see now an example of a real smart contract, some code. And I'm sorry about this, but some people have said that this resembles a little bit of Java and sometimes JavaScript. So sorry, at least to this guy I know. So a smart contract is pretty much like, at least in Solidity, which is the language used in Ethereum, or one of the languages used in Ethereum. A smart contract works pretty much like a class, which we can instantiate. In this case, let's do a simple example of creating a bank in the blockchain, where we can deposit our money and later withdraw it. This bank can have a constructor, which in this case it's doing nothing for now, but just to showcase that we can do this. We can initialize some states. We can add some instance variables to our bank. In this case, we can give it a name and we can give it a mapping, which is just kind of like a hash table, where for every address, this would be an Ethereum address, a blockchain address, we would assign an integer which shows how much that address has in the bank account at any given moment. So when people deposit money, we'll just increment the balance. When they withdraw it, we'll just deduct this balance, just to keep track of how much everyone owns. Okay, when we instantiate the bank, we can just assign the name by default. And then we can add some functions to our contract to read and to mutate that state. So we can add a function to read the balance of any user. This function has a few modifiers. So in this case, the public modifier means that the function can be called from the outside. It's pretty simple. The pure modifier means that this is a read-only function. So we're not mutating the blockchain here. We're just making a query. And this function just goes to the map, and for the address that we give it, it shows what the balance of that address is. This would, of course, all be public data, so for this bank, everyone could know knowing an address of another user would allow us to know his balance. That's just how it is. We could make this private in a way, but I'm not going to go into that right now. And then we can create functions that mutate the state of our contract. And this would be done through the payable keyword. I mean, not through the payable keyword, but through functions that just mutate that state. In this case, to deposit money, I would send a transaction to the smart contract. And in the case of Ethereum, sending a transaction and calling a function, it's pretty much the same thing. In order to call a function that mutates the state of the smart contract, we send a transaction where the data of that transaction, instead of being actual currency that we're sending, it's a special kind of data that says, call this function with these arguments. And in this case, we're going to the balance of the sender. This message.sender is a default variable that is assigned the address of whoever called the transaction. So when I'm calling this function, it's going to be my address that shows up there. And I can also, since I'm sending a transaction through the blockchain, I can also add Ethereum currency to it. This is just how the Ethereum blockchain works. I can attach some value to every currency, to every transaction that I send. And that goes to the message value. That's how much I sent in the transaction. And I'm just going to increment the balance of my account. And whatever value I sent, since I sent this transaction to the smart contract of the bank, is going to be kept in the balance of the bank. So if I sent 1 Ethereum to this smart contract, the smart contract will now own this Ethereum, and it's just going to update its own state to say that that Ethereum belongs to my address. But it's going to be the smart contracts owning it. At this point, I don't have any more control over it. And then we can, of course, have a withdraw function to do the opposite operation, where we specify how much we want to take back. Of course, we need to have enough funds in our account. In this case, I'm not even doing that. And it's going to go to the message sender and transfer it an amount equal to the amount I requested. And then deducting that balance from that amount from my balance. But this part here actually has a problem. Okay, so the first problem is that I wasn't checking prior. I wasn't checking if I had enough balance. So if you notice in this, in this first case, if I have no balance on the bank, but the bank actually had balance from some other user, so it had cryptocurrency stored in there, I could just ask to withdraw one Ethereum. And if it had some amount of Ethereum in its smart contract, not on my balance, but on someone else's balance, this would still send that Ethereum to me because I wasn't even checking that I have the correct amount. What would happen was that I would receive the Ethereum and my balance would be, this is an unsigned integer, so it would just overflow, and this would actually be a critical bug. So the way to solve that was to add an assertion to the beginning of the transaction to ensure that I have enough balance to fulfill this request. So if I'm withdrawing 1 Ethereum, I obviously need to have at least 1 Ethereum on my balance. And since all these transactions are atomic, just like any database transaction or any transaction in general, if this assertion fails, the whole transaction will fail. So either the whole thing happens at all or it doesn't happen anything. But there's still another problem here, and this problem is much weirder to notice and to solve. And that goes into how we attack smart contracts. which there are a few ways of doing it, but so first of all, we can do attacks at the consensus layer, so that layer that I talked about that we're abstracting. Even though we should trust it at smart contract level, there's still ways to attack it. So 51% attacks, I'm sure you've heard of this, are one way. Double spends, even though they're usually not possible, there's still a few caveats there, but these things are out of the scope of this talk. Again, we can talk about this later if you want. But what I wanted to get into was developer mistakes, which is actually the most serious type of problem sometimes. And I wanted to do this by telling a quick story. So let's say you're going to an ATM, just a regular Euro ATM, or in this case rubles, because I think I wrote the slides for a talk in Russia and I didn't edit them. So let's say we're gonna withdraw 1,000 rubles, which I don't even know how many euros this is, but it's very little. So you go to the ATM, you want to withdraw 1 million rubles. The ATM will start by checking your balance, and assuming you have enough money there, it's going to give you the money. And then it usually asks if you want to do anything else. And let's say you say, oh, yeah, okay, I miscalculated, just give me another million. And machine is going to check your balance, it's going to send you the money, and okay, there you go. Do you want to do anything else? And at this point, no, okay, I'm good. And so the machine will do the usual thing. It will update your balance on the bank account, and it's going to return your card. Have a nice day. Did anyone see a problem there? Yeah. Yeah. So I withdrew a million rubles. It checked my balance. Then I withdrew again. It checked my balance again. But in between these two transactions, I lost 1 million rubles. But when I checked the balance, I didn't update it before. So if I only had 1 million rubles in my account, I would be able to withdraw 2 million, and my balance would end up being minus 1 million. And this is actually what's called a reentrancy attack in Ethereum. Has anyone heard of this term before? Yeah, the two guys I work with. Okay, so this is actually how one of the most critical bugs in Ethereum usually happens, and how some of the largest hacks have happened in the past. And to show this, let's go back to the withdraw function that I've shown before. So, okay, we're checking if we have enough balance, we're transferring that amount to whoever requested it, and then we're deducting the balance. And so let's put our smart contract here on this side, and on this side let's have another smart contract called the totally legit user, which is totally not. And because I said that smart contracts are first-class citizens earlier in the talk, what this means is that smart contracts in the Ethereum blockchain, they have just as much power as we users do. We can call smart contracts, we can transact money through other accounts. Smart contracts can also do that. They can interact with other smart contracts. And it's sometimes hard to distinguish if I'm talking to a user or if I'm talking to a smart contract. Much like in Twitter, we're sometimes receiving replies from random bots. The same thing happens here. So we can create a smart contract called a totally legit user, and instead of us interacting with the bank, we can have our smart contract interact with the bank in our behalf. So let's add a function called steal to our smart contract that's going to try to withdraw 100 somethings, 100 ether from the bank, or 100 Wei, the subunit. Let's assume that we already have this balance in the bank. We deposited before. I'm just not showing that here. So when we call the withdraw function of the bank, we're going to call that function. We're going to pass in execution control to that side. It's going to require our balance, and it's going to transfer us back 100 units of money. And what this transfer does is, like I said before, sending money and calling a transaction is pretty much the same thing. So when the bank is transferring money back to us, it's actually calling a function on our side. In this case, it's not calling any function because we didn't specify a function name or arguments or anything. We're just trying to send money. And the way Ethereum handles this, which is probably the stupid part of this, is that, okay, if the transaction doesn't match any function in my smart contract, let's call a fallback function. Let's just have any non-matching transaction go to this, so that we can, in a way, this is a way for smart contracts to handle any time they receive money that they're not expecting to receive, either to raise an exception or just to say, no, this is not meant for me, I'm going to refuse this, take the money back, or just warn the user or whatever. But the point is, we're giving back control to the other guy. And the other guy can just say, okay, I'm going to call steal again. I'm going to recursively call back the function. And you notice that at this point, the part of the code that deducts my balance hasn't been called yet. So if I'm going to withdraw again, it's going to go through the same require, but my balance is still not updated. And so this creates a loop. And in this case, this doesn't work because it's just going to go around forever until the balance is negative and the transaction fails or the stack trace explodes. But if I just add a small if condition to my fallback function to ensure that, let's say, I only want to call this at most 10 times, that means that I'm going to be able to withdraw 10 times as much as I was supposed to. And at the end, the bank is going to be left with less money to fulfill the other users. Probably my balance is going to overflow, and I'm going to have, I don't know how many $1 billion on my balance there, which creates even an additional problem later on. Yeah, this is the part that didn't get called at all. And I'm guessing someone can also figure out the fix by now, except you three. So first of all, this is actually how the largest hack in Ethereum history happened. The smart contract for the DAO project in 2014. That smart contract was audited by the creator of Solidity, the guy who created this language. It was one of the largest projects in cryptocurrency space ever. And it had this exact bug, which allowed someone to steal everything and cause the fork for Ethereum Classic and cause a whole bunch of problems for everyone. And yeah, the fix, even though this function is wrong, the fix is actually pretty simple. We just swap the order. So we just deduct the balance first to ensure that the state is already done before we transfer control back to someone else. And this would actually work and solve everything. So just switching 2 lines of code would solve everything and save everyone millions of dollars. Sorry? I couldn't. No, yeah, this is not a problem with smart contracts or the blockchain. This is just a problem of developers. This is the kind of mistake that we do all the time, except that here it's irreversible because the smart contract is irreversible unless we code in some way to do updates, which is not even an easy thing to do right now. But this was just to showcase what some of the big problems are right now, which is developers. Usually we are to blame for everything. The good news is there's already a few projects as well that are trying to fix this for the developer perspective. So creating smart contract languages that are more developer friendly and where it's harder to make mistakes. Because like I said, this resembles a lot JavaScript because it actually compiles down to JavaScript and most of the tools are in JavaScript. And if anyone here has coded JavaScript, you know how easy it is to make mistakes. And when we're handling millions of dollars in a non-reversible way, I think that's not really a thing that we want to do. So they're already creating a new language, actually more than one, but this is, I think, going to be the main one in the future, called Viper for Ethereum. It's based in Python, but it has a lot of mechanisms on top of it to make sure that these kinds of mistakes don't happen, and that to make it harder for developers to make mistakes. There's also other approaches like Cardano, which is another blockchain that's is more focused on mathematically proven computations, which are made in Haskell, like any mathematician does usually. Yes. And if anyone knows Haskell or how the Haskell community operates, you also know that it's probably a much more secure project. Yeah, those are just two alternatives. Solidity is the main one right now for Ethereum. I don't love it. It's what we've got right now. But yeah, this was just to showcase really quickly how smart contracts work and how they differ from traditional programs and what their mistakes are. Thank you. And if anyone has one question, okay? Yeah. So the way they fixed it was by forking to Ethereum Classic. I don't know if you know that story. So at that point, this was a really serious problem, and the Ethereum development community, the top guys, they got together and they discussed this, and they had the idea of, okay, let's go to the particular block where the hack happened, and let's fork from this block, let's reverse the chain all the way back to this point and reverse everything that happened here. Let's launch a software update that invalidates all the blocks from this point, so that the chain starts again from the point where the hack hadn't happened yet. And this goes against all the non-reversible and decentralization things of the community. Some guys didn't agree with this for obvious reasons, and that's how Ethereum Classic came up. So Ethereum Classic is actually a copy of the Ethereum blockchain all the way up to the point of the hack, a few blocks before that. And so in Ethereum Classic, the hack happened, so all the state from that hack and everything forward remained, and Ethereum went back to the point of the hack and stayed and continued on a new chain.
So basically, both the hack and the legitimate the legitimate transactions didn't happen on the new blockchain.
On the Ethereum Classic blockchain.
So
yeah.
I guess my next question is, how didn't that break the trust in the mechanism?
It did in a way, because that was mainly it was a more philosophical debate than a technical one, because so we're creating this decentralized thing where no one has any more power than anyone else, but then these top guys decide to reverse all these things because someone messed up. And yeah, I guess we can understand why they decided to do this, because it was a clear bug, but also it wasn't.
But how do you guarantee users that it won't happen again, that you won't need to reverse it again? That there won't be another developer doing the same thing and getting millions and millions of dollars stolen, and you're going to have the same story going over again? How do they guarantee that? They don't, right?
Right now, you still don't. That's one of the things that we need to work on before using these systems for actually handling millions of dollars. Right now, they're working on things like updatable smart contracts, which there's a lot of problems that creates, but it's the thing being researched. Or just things like these languages that I talked later, that make it harder for developers to make these kinds of mistakes. More mathematically proven code. Code auditing was also supposed to be a thing, but this code was audited by the guy who created the language. Probably not basing your tools on JavaScript when you're trying to do this kind of things is also a good idea.
So
what I'm saying is there's no solution
There's no guaranteed anything. So basically what you're saying is that this is not more secure than the actual banks we have right now centralizing everything. Before you answer that, I'm a mathematician and I work in a bank.
No, but I agree with you.
Okay, thank you.
That's why I had the unhackable.
Okay, thank you.
You can see different process of things. Like, if you look at any contract, law contract that you apply between two people, and at some point you might get a lawyer that wants to disagree what is written and agreed, and you take that to court or make something that makes invalidate that contract established.
I work in a bank. We have guys like that in the same department, in the same team every day.
Not you.
I'm going to go easy on you. What's your favorite smart contract scam that you've seen?
Okay, I thought you were going to ask my favorite smart contract, which is my rock, paper, scissors, lizard, Spock that I did.
I need the answer to that.
My favorite smart contract scam? I don't think I know. I could only think about the Ethereum useless token thing. And it's not really a smart contract. It's just an ERC20 token called useless Ethereum token that raised $60,000 with a website that just said how useless it was and how many televisions they were going to buy with all that money. And it raised $60,000. I think that would be it. That or Jesus Coin.
Thank you.
One question here? You're the mic guy now.
I think we have the roles reversed.
Earlier you talked about how we could prove that the diamonds that were harvested were blood diamonds or not by somehow building a blockchain. But
You said the timing, sorry?
the diamond story, yeah. But how can you prove that the data that you put inside the blockchain, it's actually truth or not? Because in the end, we're all human beings, right? It's some kind of mechanism that needs to update or put the data in the blockchain. And when I say diamonds, it's anything else. How can we trust that the data that is in there, it's actually true or not? And because in the end, the data will be there, well, forever unless we change it. And if we change it, isn't it like we use just a regular database? And why should we use blockchain?
Yeah, that's what I was, touches on what I was saying earlier. So for example, about insurance policies, you can have a smart contract that implements what the rules of the insurance policy is for your car. But then if you hit your car, someone needs to go into the blockchain and input the data. Yeah, it was his fault. And how do you trust that that part is true? That's the part that is still, in a way, being solved. One of the solutions is to both decentralize that input so that multiple parties need to input the same data and validate each other. And the other component is to create incentives for people to not mess up that data, and disincentives for people to mess up. So one thing that's also being researched right now is the concept of oracles, which is a smart contract. An oracle in blockchain terms will be a smart contract that grabs data from the real world and puts it into the blockchain for other smart contracts to read. So you can have, for example, I think there's some betting projects where you can bet on sports games, and they use an oracle system to input the game results into the blockchain. And the way this would work was that there would be multiple oracles hosted by different miners of the blockchain. They would be independently inputting the same values. And if one of them messes up or loses reputation by inputting data that the other ones disagree, you would lose some reward, some Ethereum value that you would have to pay up front to.
Yeah.
This would be one of the possible solutions.
Yeah, well, I understand it, but if you trust people to update the blockchain, then you don't necessarily trust the data that's in the blockchain. You trust the people, right? So.
No, yeah, but that's the problem. You.
Yeah.
There's a limit to what you can do with a smart contract because of just that, yeah.
Oh, okay, yeah, that was the question.
Maybe someday someone will solve that in some way.
I think we need to trust more people. We need to be more trusted, I think. No way. I don't know. Everything can be manipulated so easily.
For example, one of.
Still a problem nowadays.
I can give a small example. The rock, paper, scissors, lizard, Spock game that I was talking about.
Yeah, I don't know.
The way that worked was that you had to, two different users had to make a transaction to the smart contract specifying its move and sending along some Ethereum as a bet. But you can't just say my move is rock and here's one Ethereum, because that data will be public and the second user could just go into the blockchain and read, okay, this guy played rock. So the way you would do that is you would hash your move along with a password, And you instead of sending rock, you send that hashed secret to the blockchain, and that gets stored. And then the other user does the same. And once both players have played, someone can call a third function that says, send the money to the winner, along with the passwords for both users. And at that point, the blockchain can grab the first user could say, I'm going to claim I played rock, and here's my password. And the blockchain is going to hash again the string rock with your password. And if it matches your move, it's going to return you the money. So in this case, the data wasn't actually there in the blockchain. I just had a way to prove that I played that move without storing that data actually there. This is a very simple example, but it's one of the simple things you can do, and the rest you can just put a pretty UI around it.